All right, welcome back everyone. In this video we're going to be taking a look at a couple more proofs. We did a few proofs in the last video. Now we're going to do a few more. Specifically, we're going to be proving a couple theorems, the midpoint theorem and the angle bisector theorem. And so first, a little review. If you remember back to chapter 1, we learned about postulates and theorems. And postulates and theorems in geometry are very similar. They're both kind of rules about things that must be true regarding certain kinds of geometric figures like angles or segments or lines or and so forth. The difference being that postulates, we just accept them as true, but we can't actually prove that they're true. But theorems, on the other hand, they can be proven true through the use of other information, previous theorems, postulates, definitions, and so forth. Now, every theorem in geometry can be proven using postulates and properties from algebra. And like I said, we're going to do a couple of those in this video today. We're going to prove a couple theorems and how we know that those specific theorems have to be true. So first of all, if you were told that T was the midpoint of segment WM, so just to get an idea of what we're talking about here, let's draw this. So let's say I have a segment here that is segment WM, so W on one endpoint and M on the other endpoint, and T is the midpoint. Now we know that in order for that to be the midpoint, it means that these two segments would both be congruent. If we knew that WM equaled 20, so the distance from W to M was 20, you would probably deduce fairly easily, I would think, that the distance from W to T would be 10. In previous classes, we talked about how that just seems like common sense. It just seems like, well, if the whole thing is 20, and I put a point here right in the middle, dividing it into two equal parts, each part is 10. But there is a theorem that says that that must be true, that if T is the midpoint of a segment called WM, then the distance from W to T will be half of the distance from W to M. And we can prove that that has to be the case. We can prove that that theorem has to be true. And so that's going to be the first thing we're going to do here. We are going to prove the midpoint theorem, which says that if M is the midpoint of a segment called AB, then AM, the distance from A to M, is half of the distance from A to B, and the distance from M to B is half of the distance from A to B. So we're going to prove that that has to be true. And we're going to start with this diagram and the information that M is the midpoint of the segment. And we're going to prove these two things must be true. So you can see here we have a two-column proof with statements on the left and reasons are going to go on the right. I've got all the statements down for you, so what we're really going to be concentrating on is figuring out what are the reasons for these statements. As we get further on in this class, we will be doing proofs where we create the statements and the reasons, but right now we're kind of taking baby steps into it, and we're just looking for the reasons. So first of all, the statement 1 says that M is the midpoint of segment AB. How do we know that? Well, because we were given that information. And remember, oftentimes proofs start with the given information. The second statement says that segment AB is congruent to MB, which is the same thing as saying that the distance from A to M, I have a little typo here, I'm sorry guys, this should say AM is congruent to MB. That should say AM is congruent to MB, which is the same as saying that from A to M is the same distance as from M to B. Now, how do I know that that's true? Based on what I just told you in statement 1, that M is the midpoint, how do I know that that means that segment AM is congruent to segment MB? Well, I know that because I know the definition of this word right here. I know what a midpoint is, right? I know that a midpoint of a segment is the point that it divides the segment into two congruent segments. So in the definition of a midpoint, it literally tells us that that point is dividing this segment into two congruent segments. So that's how definitions sometimes get used in a proof. We will look at a statement and say, well, how do I know this is true? Because I know what this word right here means. I know what a midpoint means. I know what a midpoint suggests about a picture. Now, statement 3 should look familiar. We've done statements like this before, and we've come up with a reason for this. It just simply says that from A to M plus from M to B equals the distance from A to B. And that, of course, is the segment addition postulate. That's the segment addition postulate that we've used already in a couple proofs. Next, it says AM plus AM equals AB. And we'll get to the second part in a minute. In the second part, they're just kind of combining these two like terms like we do in algebra. So just concentrate on what it says here at the beginning of statement 4. AM plus AM equals AB. Now that's similar to what we said in statement 3, where we said AM plus MB equals AB. So what's happened from statement 3 to 4 is that the MB has been turned into an AM. So we think, well, what would allow this MB to turn into an AM? Well, it's the fact that right here we said that those two things are equal, that AM equals MB, right? So if I have an MB right here, I can turn it into an AM right there. And so that is, when we turn one thing into another because the two things are equal, that is the substitution property. Substitution. Let me rewrite that because that's kind of messy. Substitution property. Very good. Okay, so next what did we do? We took this statement, which we consolidated into 2 times AM equals AB, just a little bit of combining like terms to get from the first part of statement 4 to the second part. And then we just said that AM equals half of AB. So how do we do that? How do we take this 2AM and turn it into just AM, and this AB and turn it into half AB? Well, what we did is we multiplied this whole equation times 1/2. So that half of 2AM just became AM, and half of AB became 1/2 AB. So if I multiply an entire equation by some number, that is using the multiplication property. The multiplication property. So then what we do? How do we get from... So we've proven one of our statements, right? That AM is half of AB. Well, what about the second part of the prove, where it says that MB is half of AB? Well, that's what we have in statement 6, but how do we get from statement 5 to statement 6? All we did was we changed this AM back into MB, right? Here and from statement 3 to 4, we changed MB to AM. Well, now from statement 5 to 6, we changed the AM back to an MB, again, using the substitution property. So there you have it. That's a proof of how, given the fact that M is the midpoint of a segment, that we would know that each half of that segment is half the length of the entire segment. So we just proved a midpoint theorem. Now in example 2, it says, well, given that M is the midpoint of segment AB, and N is the midpoint of segment CD, and the distance from A to B equals the distance from C to D, what other information can we deduce? Well, let's get a sketch of this, right? Because we want to try and figure out exactly what is being said here. Well, I'm going to start at the end, that AB is equal to CD. That would tell me that segment AB, if I call that segment AB, all right, so this is segment AB, it says that it's the same length as segment CD. So let's draw another segment of about the same length. All right, so segment CD is the same length as AB. M is the midpoint of AB, and N is the midpoint of CD. So I know that M has broken this into 2 equal parts, and I know that N has broken this one into 2 equal parts. But if AB started out as the same length as CD, and I cut both of them in half, wouldn't that mean that all of these are the same length, right? Well, that's what we could deduce. But then the second part says explain your thought process. So we can deduce based on this information that AM is equal to MB, but it's also equal to CN and equal to ND, that all 4 of these distances are equal. Why? Because AM is equal to MB and CN is equal to ND. But AM is equal to half of AB. And AB equals CD. So if I turn this AB into a CD, AM is half of CD. You can see all I did here was I substituted these two things for one another. Because AB is equal to CD, I can turn this AB into a CD. So AB is half of CD. If AB is half of CD, that means MB is half of CD. But I also know by the midpoint theorem, that thing we just proved on the previous page on example 1, CN is also half of CD. So if AM is half of CD, and MB is half of CD, and CN is half of CD, then I know that AM equals MB, and it also equals CN, because they all equal half of CD. But I also know that ND is half of CD, also by the midpoint theorem, right? The midpoint theorem tells me that both of these things are true. So since ND is also half of CD, ND could be put into this equation as well. Now that is actually a form of a proof. That's more of what we would call a paragraph proof. It's not a two-column proof, but it's the same idea. We stated that we know this because we know that these are true, and I guess you could say that I know that this is all true because of definition of a midpoint. I know that these two equations have to be true because it tells me that M is the midpoint of AB and N is the midpoint of CD. So that tells me that all these things are true. This is true by the midpoint theorem. And then we use some substitution to change some of these equations into other similar equations. And so that's kind of a proof. It's not a two-column proof, but it is a type of proof. Now, example 3, we are actually going to do this one in class. I will try and put up a video of me working out example 3. If you're wanting to see that, you can watch that in a little while. But right now, let's go to the last bit of the note sheet where I have here, what kind of reasons will we be using in proofs? Well, obviously, some of our reasons will be given because we're going to use the given information in any proof. We will also use definitions. We will also use postulates. And we will use theorems. And then sometimes one thing I guess you could put on here is we will also use different properties of algebra. Those things that we learned about in section 2. Properties of algebra. That would be, I guess, the 5th thing that we might use in a proof. So here's another proof that we're going to take a look at. If we are given that the measure of angle 1 is equal to the measure of angle 2. So I'm going to mark those two as congruent. That's something you should always do. If you're given a diagram and some information about that diagram, you should always make sure you mark in that picture what the given information is telling you. So I've marked angle 1 equal to angle 2, or that those two angles are congruent. It says ray AD bisects angle CAB. Well, that would indicate that angle 1 and angle 3 are also congruent. It also says ray BD bisects angle CBA, which would tell me that angle 2 and angle 4 are congruent. And my job is to prove that the measure of angle 3 equals the measure of angle 4, which I've already kind of marked. I can see now that angle 3 and angle 4 are congruent because they have the same marks, but those marks came about based on this given information. So let's see how we can prove that this angle 3 has to be equal in measure to this angle 4. Statement 1 is all the given information, right? That measure of angle 1 equals measure of angle 2, that ray AD bisects angle CAB, and that ray BD is bisecting angle CBA. So that's all the given information. Then it says measure of angle 1 equals measure of angle 3. Well, how do I know that angle 1 is equal to angle 3? How did if I think back to when I was marking this picture out, what led me to put the same mark on angle 1 and angle 3? It was this statement right here, right? That ray AD was bisecting angle CAB. And so I knew that those angles were congruent because I knew what this word meant. I knew what it meant to bisect the angle. So that would indicate that I used a definition. I used the definition of angle bisector. I used the definition of an angle bisector to say that angle 1 and angle 3 must be congruent. And then the second part of statement 2 just says that angle 2 and 4 are congruent, and that was the same reason. I marked those congruent because I knew what this word right here meant, same word as it was right here, but I knew that if ray BD bisected angle CBA, it made these two angles congruent. So step 3 takes angle 3 and makes it congruent to angle 4. Well, how do I know that that's true? Because I turned angle 1 into angle 3, right? I took, to color code a little bit here, I took, in this statement, where angle 1 was, oops, I didn't mean to use that marker, I wanted to use a different one, where it says angle 1 right here, I made it angle 3. So this angle 1 became this angle 3, and since angle 2 is equal to angle 4, this angle 2 became this angle 4. And so what did I do there? I substituted angle 3 for angle 1 and angle 4 for angle 2 in statement number 1. And so that would be the substitution property. So there you have it. There's another proof. This one's not a proof of a theorem, but it's a proof using given information, using a definition, and using one of these properties from algebra to prove that this must be true based on this information. Okay, so there is one more example here. Again, I'm going to do this one in class, so I'll post a video of me solving it, and you can watch that if you would like. Otherwise, we will cover it in class. So have a good night, everybody, and I will see you soon.